Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Product of array except self. Leetcode 238. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given an integer array nums and we should return an array answer such that answer I is equal to product of all the elements of nums except the number at ith index. The product of any prefix or suffix of nums is guaranteed to fit in a 32-bit integer, and we must write the algorithm such that it runs in on or linear time, and we shouldn't use any division operator. Then in example 1, for the given nums array, for number at index 0, that is number 1, we multiply all the elements except for number 1, which will be 2 into 3 into 4. For index 1, product of all other numbers will be 1 into 3 into 4. And for index 2, it will be 1 into 2 into 4. And finally, for index 3, product of all other numbers will be 1 into 2 into 3. So our resultant array will be 24, 12, 8, 6. Then in example 2, for the given nums array, we can see that there is a 0 at index 2. Hence, the product is 0 for every number except for this index where the product will be minus 1 into 1 into minus 3 into 3, which will be equal to 9. Now in terms of solution, one of the naive approach can be to run two nested loops, where for each element at the index I in the array, we calculate the product of all the elements excluding the one at index I. So the outer loop processes each index and the inner loop calculates the product of all elements except the one at index I. However, the time complexity of this approach will be O of n square due to nested loops, and it will likely result in time limit exceeded for large arrays. And now the question is, can we do better? And the answer is yes. In naive approach, we were calculating the product for each element from the scratch, which means repeating a lot of calculations. If division was allowed, then the solution would have been quite simpler. We could multiply all the numbers in the array to get a cumulative product. For example, for this array, the cumulative product will be 1 into 2 into 3 into 4, which will be equal to 24. And now for each element in the array, we could calculate the result by dividing the cumulative product by the element itself. For example, for index 0, result will be 24 divided by 1, which will be equal to 24. For index 1, it will be 24 divided by 2, which is 12. For index 2, it will be 24 divided by 3, which is 8. And finally, for last index, it will be 24 divided by 4, which will be equal to 6. And hence, our resulting array is 24, 12, 8 and 6. However, we need to be careful with this approach. What if one of the elements is 0? For example, we had the array 0, 2, 3, 4. Then the cumulative product of this array will be 0. And now, if we divide 0 by 0, we will get the number as undefined. So to handle this case, we have to count how many zeros we have. So if there is exactly 1 0, then all the elements in the array should be 0 except the index where the 0 is located. At that index, the result will be product of all non-zero elements. For example, the answer for indices 1, 2 and 3 will be 0 each because they will get 0 as one of the multiplying element. But the index where there is 0, that is index 0, the answer should be 2 into 3 into 4 equal to 24. And now suppose we have two zeros. For example, we have array like 0, 0, 3, 4. Then in this case, all the elements will be equal to 0 here because they will always get 1 0 as one of the multiplying elements. So in this approach, apart from calculating the cumulative product, we should also count number of zeros, and based on that, we can actually calculate our answer. And the time complexity of this approach will be O of n as we iterate over the array twice, first to compute the cumulative product and zero counts, and later on to construct the actual result array. And the auxiliary space complexity will be O of 1 because we just need the space to store the results. Here is a quick code walkthrough of the algorithm we just discussed with Java code on the left and Python on right. So first we will initialize some variables. We will create answer array of size n and total product will be equal to 1, and we'll store the cumulative product of all non-zero elements in the nums array. Let's also initialize 0 count to 0 to store the count of zeros in the array. And now we will iterate through the nums array, and for each element, if the element is 0, then we will increment the 0 count by 1. But if the 0 count is already more than 1, we can immediately return the result array filled with zeros, as having 2 or more zeros guarantees that the product at every index will be 0. Otherwise, we will multiply the current element with the total product, and once we know the 0 count and total product, in the second pass, we will fill in the answer array. If 0 count is equal to 1, then for each index where the element in the array is 0, we set the answer to total product. Otherwise, we will set the answer to 0. And if the 0 count is equal to 0, then in that case, we will set the answer as total product divided by number at the ith index. But alas, the division is not allowed. So let's observe this array a bit closely. For index 1, we need to get the product of elements on its left, which is 1, and product of elements to its right, which is 3 into 4. And this is true for any index where we essentially need to compute the product of the elements on the left side and on the right side and multiply the two sides to get our answer. And this is where prefix and suffix multiplication comes into picture. So we can create a prefix array to store the cumulative products from left up to, but not including that index. For example, here we didn't include the element 2. So we can go through the array from left to right and compute the prefix. For element at index 0, there are no elements to the left of it. So we can fill the prefix as 1, which is the minimum number we can take to do the multiplication. For index 1, the prefix will be 1 into prefix 0, which is 1 itself. For index 2, prefix 2 will be the new number we have seen on the left, which is 2, into the prefix at index 1, which will be 2 into 1 equal to 2. And finally, for index 3, it will be number at index 2, which is 3, into prefix at index 2, which will be 3 into 2 equal to 6. Similarly, we will calculate the suffix array by scanning the array from right to left and calculate the cumulative product of the elements from the right up to, but not including each index. For example, suffix for index 3 will be equal to 1 because there are no elements on the right of 4, and that is the minimum element we can take to start the cumulative product. Then suffix at index 2 will be new number seen on its right, that is 4 into suffix at index 3, which will be 4 into 1 equal to 4. Then suffix at index 1 will be 3 into 4, which will be 12. And finally, suffix at index 0 will be 2 into 12, which will be equal to 24. So this is how we will build the prefix and suffix arrays. And now let's build the answer array. For each index I, multiplying the prefix and suffix gives the result for that index. Because we know that for the given index, prefix and suffix don't include the index itself, but include the product of all the elements on the left and all the elements on the right respectively. Hence the answer for index 0 will be 1 into 24, which will be 24. For index 1 it will be 1 into 12, which is 12. Then for index 2 it will be 2 into 4, which is 8. And finally for last index it will be 6 into 1, that is 6. And this will be our resulting array. One advantage of this approach is that it is inherently robust for arrays containing 0. Since we are multiplying rather than dividing, we don't have to worry about division by 0 errors. The logic naturally handles cases with zeros by maintaining zeros in the prefix or suffix calculations. And the time complexity of this approach is O of n, because first we go through the array to build the prefix array, that takes O of n time. Then we again go through the array to build the suffix array, that takes O of n time again. And finally, to calculate the results, we again go through n elements in both prefix and suffix arrays. Hence, the overall time complexity will be O of n. And in terms of space complexity, it will be O of n for storing the prefix and suffix products. Here is a quick code walkthrough of the algorithm we just discussed with Java code on the left and Python on right. First, let's create the prefix and suffix array of size n and initialize the first element in prefix and last element in suffix to 1. Now we will fill in the prefix array. So we iterate through the array from left to right, starting at index 1 and calculate the prefix as product of the element immediately to the left of the current index and the cumulative product of all the elements before the index I minus 1. And then we will fill in the suffix array from right to left, starting with index n minus 2, where for each position I, we will calculate the suffix as product of the element immediately to the right of the current index and the cumulative product of all the elements after index I plus 1. And once we have filled in both prefix and suffix arrays, we will fill in the answer array by going through each index in prefix and suffix arrays and calculate their product as our answer. And now the question is, can we do better? And the answer is yes, we can definitely be more space efficient. So if we notice, in any case we have to return the answer array containing the product of the elements except self. So how about instead of creating separate prefix and suffix arrays, can we somehow use this answer array to store these intermediate results? This will remove the need for extra auxiliary arrays. Here's how we can do that. Now let's get rid of this prefix array and let's use it as answer instead. So in the first pass, we will iterate over the array from left to right to calculate the prefix products like we did in the previous approach. So for index 0, prefix will be equal to 1 because there is no element on the left of it. Then for index 1, prefix will be product of prefix at index 0 into element at index 0, which will be 1 into 1 equal to 1. Similarly for index 2, prefix will be product of prefix at index 1 into element at index 1, which will be 1 into 2 equal to 2. And finally for index 3, prefix product will be 2 into 3 equal to 6. So far so good. And now for the suffix product, we will do the same thing from right to left to calculate the suffix product. And now the answer array is filled with partial answers. So we cannot use it as a temporary array to fill in the suffix values. And so instead of using a separate suffix array, we can create a suffix variable to hold the cumulative product of numbers to the right of the current index. Initially that index will be index 3 and the suffix will be equal to 1 because there are no elements to the right of the last index. And we move from right to left and multiply the value of the result array at each index by the suffix value. So let me rewrite the answer here for clarity, but we are using the same answer or result array. Now the answer for index 3 will be product of prefix at index 3 into suffix at index 3. We already have filled in the prefix as 6 and suffix is equal to 1. So our answer will be equal to 6 in this case. And now we will update the suffix by multiplying the element at index 3 into the current suffix, which will give us 4. Now for index 2, our answer will be product of prefix at index 2, that is 2 into current suffix, that is 4, which will be equal to 8. And after this, we will update our suffix by multiplying the number at index 2 into current suffix, which will be 4 into 3 equal to 12. Similarly, for index 1, we will multiply the prefix at index 1 into current suffix, which will be 1 into 12 equal to 12. Now we will update the suffix by multiplying the element at index 1, which is 2. So our suffix will become 12 into 2 equal to 24. Now for index 0, our answer will be prefix at index 0 into current suffix, which will be 1 into 24 equal to 24. So our answer will be 24, 12, 8 and 6. And now the time complexity is still O of n, because in the first pass we are calculating the prefix product of all the elements in the array, which takes O of n time. And then in the second pass, we are multiplying it with the suffix, which again takes O of n time, resulting in overall time complexity of O of n. However, the space complexity now will be O of 1 if we exclude the output array. Now let's go through the code together. First, let's create an answer array of size n to store the final results. Now we will fill in the prefix product first. So let's create the variable prefix equal to 1. This will be used to calculate the product of all the elements to the left of the current index. Now we will start iteration on the array and store the value of the current prefix at ith index and update the prefix by multiplying the current element for the next index. And once we are done with filling the prefix, we will do the same thing with the suffix. So initially we will again set the suffix equal to 1. This will hold the cumulative product of all the elements to the right of the current index. So now we will iterate from right to left, and for each index I, we will multiply the current value at index I, which already contains the prefix product, by the current value of suffix. This combines the prefix and suffix product for index I, giving us the final answer for that index. And after this, we will multiply the suffix with the current element so that it can be used for the next iteration. And once we are done with both the loops, we will return our answer. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.